Hello, I'm Stuart Reid. Welcome to this session of the AI testing course. In this session, we'll give a basic introduction to artificial intelligence. From now on, I will normally refer to artificial intelligence simply as AI. For those of you who have familiarity or exposure to AI, some of the material may be familiar to you, depending on your familiarity and exposure to artificial intelligence. The idea is to give you a basic foundation for the rest of the course. On this slide, we can see from the Oxford Dictionary definition that intelligence is about the ability to acquire and apply knowledge and skills. We normally do this to solve problems. We all have this ability, and most people would agree that animals also have this to different extents. For instance, rooks from the corvid bird family, elephants and dolphins. So, what changes when we move to talking about artificial intelligence? Well, not much. The definition of AI says acquire, process and apply, but processing is probably implicit in the first definition. The main difference is the inclusion of the term engineered. The definition of intelligence is normally applied to natural organisms like people and animals, whereas AI-based intelligence forms part of an engineered or manufactured system. Of course, as it says on the slide, we can also use artificial intelligence to refer to the discipline of developing and studying AI-based systems, much like we are doing on this course. A curious phenomenon around AI is known as the AI effect. This effect is concerned with how our perceptions of what is meant by AI have changed over time. One part of this AI effect is that we tend to conflate the ideas of AI and complexity in computer systems. If we were to look back about 50 years, what we today consider to be very simple computer systems were considered to be extremely complex and often viewed as AI. For instance, Freddy and Freddy 2, as shown on the slide, signified state-of-the-art AI in the early and mid-1970s. Freddy was built by researchers at the Department of Machine Intelligence and Perception, which was later the Department of Artificial Intelligence, at the University of Edinburgh. Freddy was one of the earliest robots to integrate vision, manipulation, and intelligent systems, using a TV camera, computer-controlled arm, and moving table to make simple assemblies, such as the 7-piece toy car shown on the slide. It could separate parts in a pile, recognize the parts using the camera, and then assemble them into the required assembly. However, if what it was assembling changed, it required a day's worth of new programming by the researchers. Would we consider such a system as AI today? Most people probably wouldn't. Another example, this time from about 25 years ago in 1997, is the Deep Blue computer program from IBM, which beat the then world chess champion Garry Kasparov. In its day, this was considered to be AI, but nowadays, because of its brute force approach and lack of self-learning, Deep Blue is considered by many to not be true artificial intelligence. It appears that our understanding of what is meant by AI changes over time, and only brand new and complex technology is labelled as AI, while technology we have come to understand becomes relegated to something less than AI. A non-stop source of ideas on AI, and often misinformation, is fed to us by cinema. Many people are informed on the potential benefits, but mostly pitfalls, of AI through what we see on the screen. On the slide are 3 examples, some or all of which you may be familiar with. Which one do you think is the odd one out? Well, WALL-E at the bottom left is a candidate, as it promotes the view of a friendly AI, looking after the planet, while in many films robots are killing machines. Alternatively, the odd one out could be 2001: A Space Odyssey, as the AI in this film, HAL, is not a physical robot, but instead is confined to the computer core of the spaceship. AI in films is nearly always in the form of a robot, and so able to move around, and it is also normally humanoid in appearance. Although HAL is not a humanoid robot, it is, however, like most AI in cinema, the baddie, as it kills the astronauts it was supposed to care for. The quote on the screen, "I'm sorry, Dave," is spoken by HAL when it locks the astronaut Dave out of the spaceship. Some of you may be interested to look up how HAL got its name. What we can see from all these examples is that the movies are very happy to guess how AI might look in the future, and they mostly seem to think it will come in the form of a humanoid robot that hates humans. We will see later in this section what the experts think of the idea of AI taking over the world. But one thing is clearly wrong with this movie vision of the future. Most AI will not come in the form of humanoid robots, but will be confined to network computers. Artificial intelligence can be thought of as being implemented by artificial intelligent agents, or intelligent agents, or just agents for short. Such agents act based on available information and make decisions based on their experiences. This means that they implement a form of autonomy, as they can make decisions for themselves. On the slide, we can see two forms of intelligent agents: robot agents and software agents. Robot, as a term for artificial automata, similar to how we use it today, was first used by the Czech writer Karel Čapek in his 1920 play RUR. We make the distinction here between robots as intelligent agents with a physical presence and software agents, which are restricted to computers and have no physical presence that we can see. Slightly confusing is the fact that we refer today to some software agents as bots. For instance, most of us will have experienced interacting with chatbots, often when we do not want to. However, having made this distinction, in terms of AI technology, software agents and robot agents typically only differ in how they interact with their environment. The underlying AI is often very similar. On this slide, we can see some examples of how AI is used in our daily lives on a regular basis. Smartphones and smart speakers now come with intelligent assistants. These can understand our speech, analyse our questions, look up the answer, and then speak the results back to us. Such assistants alone use several different forms of AI, including speech recognition and searching the internet. On its own, Google Search is an advanced form of AI. In fact, if we search in late 2021 for the term artificial intelligence, then Google Search is able to return a potential 3.6 trillion results in just over half a second. And if you're in any way unsure as to whether AI is an expanding field, the same search 3 years before in 2018 would have been equally fast, but would have returned only 69 million hits. Some applications absolutely need AI to function effectively. For instance, the Mars rover cannot be properly controlled by humans, as any radio signals used for remote control take so long to get there and back. The round-trip time for a signal is something between 8 and 48 minutes, depending on the relative positions of Earth and Mars. So we need AI built into the rover to allow it to make its own decisions at times. In March 2016, Lee Sedol, the 18-time World Go champion, and AlphaGo, a program developed by Google DeepMind to play Go, demonstrated how well AI has advanced. AlphaGo won 4-1 in a special Go match, with AlphaGo later being awarded the highest Go Grandmaster rank of Honorary 9th Dan. Immediately following this match, the South Korean government announced a 1 trillion won, or $860 million investment, in AI research over the following 5 years. Today's most complex and leading-edge AI-based systems are limited to handling a single problem area. AlphaGo, which we just mentioned, is a good example. It has taught itself, with some help from Google, to play Go as well as, if not better than, the best humans. But it cannot do anything else. It cannot tell you what the weather is outside. It cannot navigate your car. It can't recommend what song you should listen to next. And it cannot even beat you at chess. Today's AI is known as narrow or weak AI and is limited to a single application area where it has been trained extensively. However, even though we may refer to it as weak, it is often still capable of being better or faster than a human in its specialist area. Sometime in the future, we can expect to see the next generation of AI, known as general or strong AI. General AI will not be constrained to a single task, but will be able to reason and make decisions equivalent to a human across a whole range of domains. It is called general AI as this form of AI will not have specialist skills, but will be able to generalize its skills and perform in multiple areas, even in areas where it has no prior experience. On the next slide, we will get an idea of when we can expect to see AI-based systems capable of human-level generalized intelligence, assuming, of course, that there is no backlash against the technology. On this graph are the results of a survey of AI researchers at one of the main AI conferences in 2016. They were asked about their views on the likelihood of general AI occurring, which they called high-level machine intelligence, or HLMI. Each individual respondent estimated the probability of high-level machine intelligence arriving in future years. Taking the mean over each individual, the aggregate forecast gave a 50% chance of high-level machine intelligence occurring within 45 years. That would mean we could expect to see it in 2061 on average, but with a 10% chance of it occurring within 9 years, or by 2025. As is often the case, there were regional differences. For instance, Asian researchers expected general AI to happen far sooner, in 30 years on average, whereas North American researchers expected it to happen in 74 years on average. A later 2019-2020 survey of a similar group provided consistent results for HLMI. In 2016, the researchers predicted an AI agent would be able to beat human poker players by mid-2021 and beat human Atari gamers by late 2033. Actually, these benchmarks were achieved in 2019 for poker players and 2020 for Atari gamers. One of the areas covered by the survey was whether respondents felt that achieving high-level machine intelligence would result in a bad or very bad outcome. And by very bad outcome, we mean an event that would lead to human extinction by the AI. As you can see, 15% felt that this was likely. By 2020, a slightly lower 12% thought this. Given these figures, you would expect that many people in the research community are actively working to make sure that a bad outcome does not come about. At present, we're in the situation shown on the left of the slide. The red human is shown as far larger than the robot representing AI to indicate humanity's higher relative intelligence and power. As we heard from the AI researchers, this state will not last that long into the future. At some point, the capabilities of AI-based systems will have improved to a level where they are comparable with humans. It is at this point something really interesting, or scary, depending on your point of view, could take place. If these latest, most capable AIs are allowed to use the internet, then they will potentially have access to nearly all available human knowledge, along with almost unlimited processing power and storage. Thus, there is the possibility for a runaway reaction of self-improvement cycles, whereby a self-learning AI could gain in intelligence as it exposes itself to more information and accesses more computing resources. Very quickly, such a system could undergo an intelligence explosion, resulting in a powerful superintelligence that would, by then, have overtaken human intelligence. The point at which general AI starts self-improving in such a rapid way is known as the point of technological singularity. It raises the tricky question of whether a general AI should be given access to the internet with all the information, memory and processing power available there. At this point, we will introduce some of the technologies used to implement artificial intelligence. Data scientists need to be able to select the most appropriate technology or technologies to use for a particular problem, and so they need to understand these technologies in depth. Obviously, they need to be able to implement them, but they also need to know the benefits and disadvantages of each of them, so they can make an optimal choice. For the rest of us, this slide provides a high-level view of what is available, which is a reasonable starting point. Let's take the example of a software tester who tests AI-based systems. The tester does not choose the most appropriate AI technology, and so has no need to be able to compare each of the possible technologies. On the other hand, they often need in-depth knowledge of the technology they are testing. So once they know, for instance, that the AI-based system they are testing is based on deep neural nets, then they should ensure that they know how deep neural nets work and the most common and high-risk defects. But until then, in-depth knowledge of neural nets or any other of these technologies is probably not needed. In case you're worried that you'll come away from this course with no details on how these technologies work, don't worry. Because it is currently the most popular approach, this course concentrates on machine learning and will provide you with experience of building and testing several machine learning systems using various technologies, including decision trees, random forest, neural nets and rules engines. So what do we mean by machine learning? Machine learning is based on the use of computer algorithms to build a second program known as the model. This model is built by using examples provided to the algorithm in the form of training data. The algorithm looks for patterns in the data and creates a model that can recognize these or similar patterns in future data fed to it. The automatically produced machine learning model can then make predictions in the future when it is presented with previously unseen situations. Machine learning algorithms are now widely used in a variety of applications, such as in speech recognition and computer vision, where conventional computer programs have been found to be ineffective or inefficient or both. As you can see from the slide, machine learning is not the only way to implement AI. There are several other options that are useful in specific situations, which we'll briefly look at. Fuzzy logic is similar to Boolean logic, which works with just true and false. But fuzzy logic can work with the concept of partial truth, where everything is not purely black and white. With fuzzy logic, instead of just the two options of true and false, we are able to represent partial truths as real numbers between 0 and 1, such as 0.4 and 0.75. Search algorithms work on the basis of determining how to reach a goal from a starting state by navigating through a number of intermediate states. The algorithms can vary in complexity. For instance, with an uninformed search, we don't know the cost of transitioning between states, while with an informed search, each transition has an associated cost. Almost any AI problem can be addressed using search algorithms. As with anything, they are not always the optimal approach. Finding the shortest or cheapest path through a network is an example of a typical problem for which we would consider using search algorithms. Reasoning techniques describe a very general concept of rationally inferring facts from existing data, but, as you can see from the slide, can be implemented in various different ways. As with many fields, there is normally an option of combining technologies, and AI is no different in this respect. In machine learning, this is normally known as a multiple classifier system. This has been the session in which I presented a simple introduction to artificial intelligence. Thanks for listening, and I look forward to seeing you next time.